In our last episode, we talked a little bit about if I have two devices, one has information that it knows to be correct, and it's sending that information to a second device. How does the second device know something didn't happen along the way, in transit? Well, the same could actually be said for the device that has the data. How does it know that everything is correct? It stored something to memory. Then it forgot about it. Then a little while later, it comes back and it retrieves that from memory. Is it possible that something got flipped, something got changed inside there? Well, it turns out that it is possible. A stray gamma ray, maybe a defect in the silicon, something could flip a bit, change something so that we are working with corrupted data. How do we detect if the data has been corrupted? Well, we're going to talk now about something called Hamming code. Now, Hamming code basically says, along with the data, we store check bits. Some sort of a mechanism that allows us to see if this data is correct. Well, how do we do this? Turns out parity will work for us here too. Let's do something real quick. Let's say, and I realize that 4 bits of data does not seem a lot. Heck, we can only store 16 possible patterns of 1s and 0s with this, right? And what we're going to do is we're going to store along with it 3 data bits. Well, once again, not data bits, they're check bits. And these check bits are actually in the form of parity flags. And I'll show you in a minute how it's really easy in order to determine these parity flags, how we can calculate them pretty easily. All right, now I'm going to label these guys D0, D1, D2, D3. All right, and parity, let's just do P0, P1, P2. All right. And yes, we're going to use parity bits, just like we were talking about in the last episode. This time, though, it's going to be set up so that it's always even parity. I'll show you how that works in a minute. All right. Now, whenever we do this computation, what we'll do is generate these parity bits based on different groupings of the data bits. For example, remember I said that even parity is generated with the exclusive OR of an operation. So I could say that parity bit 0 is generated by the exclusive OR of D0 with D1 with D3. All right? Now, the goal is to make different groups so that if the parity flips, if certain parity bits flip, we'll know which bits got flipped in the data. Let's say parity 1 is equal to, I don't know, how about D1 exclusive ORed with D2 exclusive ORed with D3. All right? And then parity 2, this guy is the exclusive OR, we'll just say D0 with D2 with D3. All right? Now, how does this help us? Now remember that what happens is each one of these parity bits is going to be set so that the total number of 1s for that whole line is an even number, right? So, for example, if I have, in fact, let's just go ahead and come up with some data here. How about we do 1, 0, 1, 1? Can we calculate what the parity bits are? Well, let's do P0 first. P0, that's D0, which is a 1, exclusive ORed with D1, which is a 1, exclusive ORed with D3, which is a 1. So there are 3 1s, it's an odd number, that's a 1. So we put a 1 in parity bit 0. Now, parity bit 1, that's D1, which is a 1, exclusive ORed with D2, which is a 0, exclusive ORed with D3, which is a 1, even number of 1s, that's a 0. So a 0 goes into P0. Then P2, this is equal to the exclusive OR of D0, 1, exclusive ORed with D2, which is a 0, exclusive ORed with D3, which is a 1, that's also an even number, so P2 is an even number 0, right? So we store those 7 bits in memory. Now, those bits come back to us. We read these bits, but let's assume that one of the bits got flipped. Let's say that D1 was flipped to a 0. All right? Now let's do our calculation again. We don't know the original value. All we know is we're going to calculate P0, P1, P2 again. And in the space that I've got left on this board, let's try this. So P0 is equal to, well, remember it's D0 exclusive OR with D1 exclusive OR with D3. So it's 1, 0, 1. So 1 exclusive ORed with 0 exclusive ORed with 1. That's equal to a 0, right? Now, we look at P1. P1 is equal to D1 exclusive OR with D2 exclusive ORed with D3. So it's 0, 0, 1. So 0 exclusive ORed with 0 exclusive ORed with 1, which is equal to 1. All right? Now, we figure out what P2 is. P2 is equal to, let's see, P2 is 0 exclusive OR with D2 exclusive OR with D3. So 1, 0, 1. So 1 exclusive ORed with 0 exclusive ORed with 1, which is equal to 0. All right? Now, after this computation, what we've determined is our new P0, P1, P2. Our new ones are actually 0, 1, 0, right? So P0 is a 0, P1 is a 1, P2 is a 0. Now, which parity bits changed? 2 of them changed, right? P1 changed and P0 changed. P2 didn't change. So which one of these data bits, which one of these 4 data bits is a member of P1 and P0, but not P2? Well, if you look at this list right here, we see that D1 is contained in both P0 and P1, so flipping that is going to change those 2 parity bits. But it's not a member, D1 is not a member of P2. So its P2 should be unaffected, and P2 was unaffected. All right, let me try that again real quick. What happened was when we flipped one bit, one of the data bits, by flipping one of the data bits, it changed some of the parity bits. And the parity bits it changed were P0 and P1. We know this because those are the only 2 expressions that D1 is connected to. So whenever we look at our data that we've read, so what we did was we read 1, 0, 0, 1 along with those 3 parity bits. We calculated new parity bits. I should probably put a prime here or something to indicate that these are not the same as the parity bits that we had stored. We compare our calculated parity bits with our stored, or the ones that we retrieved. We see that 2 of them were different. D1 is the only one that's a member of just those 2. We know that D1 needs to be flipped back to correct the data. Let's try this graphically to give you a little bit better idea, because that was a little overwhelming, right? Let's try this graphically to give you a better idea of exactly how this is supposed to work. I'm going to use a Venn diagram to describe the operation of this 4 data bits with 3 parity bit version of Hamming code. I'm going to make some circles here. All right. Now, each one of these circles, the overlaps are going to show where the data bits are. For example, this circle right here, we're going to call group 1. And group 1 has 3 data bits in it. If you remember, we had P0, we should probably have called it group 0, huh? So group 0, P0 was actually made up from the exclusive OR of D0, D1, and D3. So what we're going to say is that P0 is D0, D1, and D3. All right? Now, you may wonder why I put D3, selected D3 to go in the middle. If you remember from our expressions, D3 was the only one that was in all 3 groups. All right? Now, in this group right here, P1, what I'm going to have is P1 is going to have, if you remember its expression, in its group it had D1, D2, and D3. All right? And then P2, the last one, we're going to have P2 is going to have in its group D0, D3, and D2. So let's go ahead and do a Venn diagram filling in the values that we used for our data up here. So we had D3 was equal to 1. So there's a 1 there. D2 was equal to a 0. Well, D2 goes in this location. That's a 0. We see that D1 originally was a 1. We'll flip it back whenever we do the errors here. D1 was a 1, so this top one right here was a 1. And then D0, this last overlapping location, was also a 1. So there's a 1 there. All right. So now let's calculate our parity. And in this case, instead of doing it with the exclusive OR expressions, let's just do it graphically. Let's look in the circle, see whether we have an odd number or an even number of ones, and set our parity so that it matches. So we have this circle right here has 1, 2, 3 ones in it. 3 is an odd number, so the parity bit for P0 needs to be a 1. This circle right here, that circle has an even number of ones. 1, 2 ones. Its parity bit should be a 0. This circle right here has 1, 2 ones. That's an even number, so its parity bit should be a 0. And we notice we get 1 for P0, 0 for P1, 0 for P2. So it works out correctly. All right, now we store this data. Remember, we have to store it all together. Whenever we get it back, though, remember that D1 got flipped to a 0. All right, now we look at this circle right here. And this circle says, each one of the circles here. This circle right here, 1, 2, 3 ones, there's a problem in that circle. Because remember, the circle, the whole circle has to have an even number of ones. This circle right here has 1, 1. That's an odd number. There's a problem there. This circle right here, 1, 2 ones. That's okay. So there's no problem there. So we need to look at this Venn diagram and see, okay, which circles have problems, which ones don't. The places where the bit that is a member of the circles with problems but not a member of the circle that's okay, that's the one that got flipped. And we see that this circle and this circle share those two positions. But since D3, the middle one, is also in a circle that did okay, that successfully had a parity check, we know that the bit flip is in that circle right there. So we know that that should be changed to a 1. All right? And there you go. Now, a couple of things real quick. First of all, like parity, whenever we talked about communicating between two devices, if I have 2 bit flips, I've got a problem. I'll show you in a minute how we fix that. But the other thing is that the data that you get back, and remember, this is exactly like the deal whenever you were transmitting between two devices. You don't know what the original data was. Yes, this data was stored in memory, in your memory, but whenever you get it back, you have no idea of which bits, if any, got flipped. So what I'm going to do is I'm just going to go ahead and say, let's see, we got some bits back. All right, there you go. I read back my data bits. I know which bits. I know from the position which bits go in which piece of this Venn diagram. So I got my data back. 1, 2, 3, 4. There's my data bits, right? And then I've got my parity bits, these bits right here. All right. Now, tell me which circles have a problem, which circles don't. Looks like this little example that I made up is going to look familiar. But anyway, this circle right here, 1, 2, 3 ones, there's a problem in this circle. This circle right here, 1, 2, 3 ones, there's a problem in this circle right here. This circle right here, 1, 2 ones, that circle is okay. So what's a member of the top 2 circles but not a member of the bottom circle? You got it. That same poor D1 keeps getting changed. It was a 1. It needs to be a 0. Flipping it to a 0 makes everything correct again. Let's try one more example. All right, let's do some more data. And let's go ahead and figure this out so that maybe I don't get D1 hassled again. So let's see, let's do this and that. There you go. All right. Now, this is the data you read back from memory. Tell me which circles have a problem. Well, this circle has 3 1s in it. There's a problem with this circle. This group right here, 2 1s, it's okay. This circle, 2 1s, it's okay. What does that mean? None of the data bits are a member of a circle that's every single one, excuse me, let me try that again. Every single one of the data bits is a member of a circle that's okay. So nothing changed with the data bits. What changed? Well, it turns out in this case, it just happened to be a parity bit that flipped. That 1 bit right there flipped, and all we need to do to correct it is simply flip it back in order to make it so that our parity, if we're going to store it again, you don't really need to correct the parity bit, but in case you need to store it again, we know what data to change. Now, let me do another example here. There's my valid groups. Okay, so I have 1, 2, 3 groups for storing 4 data bits with 3 parity bits. I have an even number of 1s in this circle. I have an even number of 1s in this circle. I have an even number of 1s in this circle. What happens if 2 bits flip? Let's go ahead and flip 2 bits to see what the change is. I'm going to flip this guy and this guy. So now I have 0 and 1. All right. Now, 2 bits flipped. I have bad data. Turns out I had bad parity too. But we don't know that. All we know is we got this back. Now I have put these two are the ones that are in error. What happens? This circle, 1, 2 1s, this guy's okay. This circle, 1, 2, 3 1s, it's bad. This circle right here, 1, 2 1s, looks okay, right? So what's a member of this circle but not these 2 circles? That 1 right there. So we think that it was a parity bit that got flipped, and we flip it back. Didn't work, did it? Right now I've got I've got 3 bits that have changed, okay? The data didn't get corrected. Now, what would be good is if I can't correct this data. This is just something that I'm going to have to say, okay, memory was corrupted, I'm going to have to give up. But do I have a way of detecting if those 2 bits got flipped? Do I have a way of just simply saying it's an irretrievable error? Well, it turns out that we do. And we do by having 1 more bit, kind of a global parity. This global parity bit is going to be used to check the parity for the whole circle, for the whole diagram. And so we just simply add 1 more bit. I'm going to just call this P sub G. All right. Now let's take a look with the data that we've already got, see how it works with the global parity bit. So I'm going to draw another one of these Venn diagrams. All right. And we're going to use this data over again. So what do I have? This is D0, so we have a 1. D1 has a 1, the original data. D2 has a 0. D3 has a 1. And then we do the parity bits. We've already done this for this same data, but we're going to do it again. So we have 3 1s in this circle. To make it even, we put a 1. We have 2 1s in this circle. To make it even, we put a 0. To keep it even, we put a 0. In this circle, we have 2 1s, so we put a 0 to make it even. Then we also have this global parity bit. Now the global parity bit is designed, once again, to count all the 1s in the Venn diagram. I have 1, 2, 3, 4 1s. That's an even number, so we put a 0 here, and our global parity bit is a 0. Now, what happens if we flip 2 bits? Well, let's go ahead and, I don't know, let's just pick 2. Let's just grab good old D1 here, and how about D2? And we're going to change those so that they are, what did we say? D1 is going to become a 0, and we're going to have D2 here. That'll become a 1. Those will flip. All right, that's it. We've stored the data, and while it was stored, these changes happened. So, can we fix it? Well, let's see. If I count the number of 1s in this circle, I've got an odd number. So something is wrong in that circle. I count the number of 1s in this circle, it's an even number. So this circle is okay. The number of 1s in this circle, 1, 2, 3, that's an odd number. So the problem is in this circle. And so using our method for correction, and notice something, I ignored the global parity bit. We haven't even talked about the global parity bit. Don't look at the global parity bit until after you've attempted a fix, after you've attempted a repair. In fact, if those look fine, then don't worry about changing anything. Assume that the global parity bit either got flipped or is okay. Just don't look at the parity bit until you've already gone through the processes of looking at the 3 parity bits with the 4 data bits. So we've got 2 errors. These 2 circles have errors. This one's okay. This guy right here, D0, is the only bit that belongs to these 2 circles, but not this one. So we flip it. We fix it, right? Okay, now that we've fixed it, we take a look at the whole thing. We've got 1, 2, 3. In the whole Venn diagram, we've got 3 1s, including the global parity bit. So that means that there is a problem. We have 2 errors. Now, this brings us to exactly what the what this is called. The whole operation of using the Hamming code with the parity bits and the global parity bit is referred to as single error correction, otherwise known as SEC, double error detection, DED. All right, so this Hamming code gives us the ability to correct a single error, bit error, or detect if 2-bit errors have occurred. Let's do another example real quick. All right, we have read memory. And out of memory, we have received the following pattern of 1s and 0s. How about 1, 0, 0, 0, 0, 1, 1. And we'll do 1. All right? Now, this is what we read. So we read a byte. 4 of those bits were data bits. 3 of the bits were those group parity bits. And then we had the 1 bit that was a global parity bit. Do we have a problem here? Well, let's take a look. In this circle, I have 1, 1. So there is a problem in this group. In this circle, I have 1, 1. There's a problem in that group. In this circle, I have 1, 2 1s. This group is okay. Remember, we start out, we ignore the global parity bit. We just try to fix it. So I've got a problem in this circle, a problem in this circle, no problem in this circle. It looks like poor old D1 has gotten it again. So this right here, that bit right there is the only bit that is a member of this group and this group, but not this group. So we flip it. And after we flip it, we get a 1 there. Now, after we've corrected it, we check against the global parity bit. And we've got 1, 2, 3, 4, 5 1s. That means that there was a double error, and then this data is considered corrupted and not retrievable. We can't correct it. All right? So there you go. Another example of how we can use this idea of parity, group parity bits and a global parity bit, in order to detect an error and even correct it if only 1 bit has changed. In the next episode, we're going to take it a step further and at least formalize some of this theory so we can start developing larger and larger Hamming codes to correct our data.